today's lecture we will discuss several important results. Let us briefly review what we have discussed so far. We have been discussing quantization of a real scalar field or a Klein-Gödel field. So, the fields are basically operators with the commutation relation phi of x t and pi of y t. Commutator is given by I delta x minus y, and using this commutation relation we have seen that the Hamiltonian for the real Klein-Gödel field, which is given by half pi x square plus grade phi square plus m square phi square d cube x. This can be expressed in terms of operators a k and a dagger k, which appear in the expansion for the field phi. So the field phi x t is written as a d cube k over 2 pi cube 2 omega a k e to the power minus I k dot x plus a dagger k e to the power I k dot x. We substitute this expression for phi and grade phi and pi in the Hamiltonian, and when we do that, what we have seen in the last lecture is that the Hamiltonian can be written as integration d cube k over 2 pi cube 2 omega times omega times a k a dagger k plus a dagger k a k. This is the Hamiltonian. So, we will start with this Hamiltonian and then we will find the spectrum for the system. So, let us rewrite the Hamiltonian in the following way. H is this times, here what I will do is there a half here? I will write it as twice a dagger k a k. So, I have added, I wrote this term and I have added one more term like that. So, I have to subtract that plus a k a dagger k minus a dagger k a k. So, I have done something which is utterly trivial. I just added this and subtracted this piece. So, this is what is the Hamiltonian. But now, you can see that in the second line I have the commutator of a k and a dagger k. So, let us rewrite the Hamiltonian. This is d cube, there is a half here, d cube k over 2 pi cube 2 omega times omega, this half will cancel this 2. So, I have a dagger k a k, and then this one is the commutator of A k A dagger k. There is a half here. That is all we get for the Hamiltonian. But now you see the second term, which is actually a commutator, is actually a C number. So, we will discuss the detail about the second term in a moment, but for the time being we will just ignore this term. This is just a C number. So, it is enough to find the spectrum for the first term here. If I find the spectrum for the first term, I find the spectrum for the full Hamiltonian. So, let us now focus on the first term. So, let us write the first term. In the Hamiltonian, which I will denote as H n. So, H n is d cube k over 2 pi cube 2 omega times omega a dagger k a k. Let us assume that E is an eigenstate of this operator with eigenvalue E. So, H n acting on E gives me E as an eigenvalue. The question that I would like to ask is, if I consider this state here, which is A k acting on the eigenstate E. So, this is some state. What do I get by acting this operator H n on this state? This is what I am interested to find. So, let us act H n on this state. Here, because I am using this label k here, I will use k prime as the integration variable. So, this is integration d cube k prime over 2 pi cube 2 omega prime times omega prime a dagger k prime a k prime, this acting on a k e a k I have to find what I get from this expression. Now, look at these two terms. A k and a k prime commute with each other. So, I can just move it to the left, and when I do that, what I will get is integration d cube k prime over 2 pi cube 2 omega prime times omega prime a dagger k prime a k prime acting on the state E. Now, these two terms, which is a dagger k prime a k, this I will write as a commutator. This I can write it as a k a dagger k prime minus the commutator of these two terms, minus commutator of a k a dagger k prime. And the commutator is nothing but 2 pi cube 2 omega k times delta k minus k prime. So, this is equal to a k a dagger k prime minus 2 pi cube 2 omega delta k minus k prime. So, this is what I will substitute in this term here. So, when I do that, I will get two terms. So, let us write both these terms separately. I have H n acting on a k E is equal to and then omega prime, then a k, a dagger k prime, then a k prime acting on E, and the second term is minus integration dq k prime over 2 pi cube 2 omega prime times omega prime, then 2 pi cube 2 omega delta of k minus k prime a k prime acting on E. So, let us look at the first term first. Here all these are numbers and this operator a k, the argument is k, whereas the integration variable is k prime. So, I can take this a k to the extreme left outside the integration. So, when I do that, what I get is a k times integration dq k prime over 2 pi cube 2 omega prime a dagger k prime a k prime acting on E. Then I have the second term, I can, because there is a delta function, I can carry out the integration. When I carry out the integration, this 2 pi cube will cancel, this 2 omega prime will cancel here, and this will simply give me omega minus omega times a k acting on E. Now, what is this term here? This is h n. So, I can now write this as a k h n acting on E minus omega a k E. No, because I have carried out this integration here, right? Here? Where is omega prime? There is omega prime here. There is one more. No, oh, this omega prime here cancelled this. Are you talking about the first line or second line? First line. Here there is a omega prime. Okay, thank you. So there is an omega prime. So the entire thing is the first term in the Hamiltonian, which I denote as Hn, and the second term is as it is. So you're right, I forgot to write this omega prime here. Okay, now look at this term. We have assumed that E is an eigenstate of Hn with eigenvalue E. So this term now is written as, I can rewrite it as E times this. So the whole thing is equal to E minus omega a k acting on E. So what we have learnt from here, if E is an eigenstate of Hn with eigenvalue E, then Ak acting on E is also an eigenstate of Hn with eigenvalue E minus omega. This is what we have learned from here. Therefore, this Ak is an annihilation operator. it annihilates a quantum of energy omega in this state here. Similarly, if you consider instead of a k acting on E, if you consider a dagger k acting on E, you will see that this again will be an eigenstate of H n with eigenvalue E plus omega. Therefore, a dagger creates a quantum of energy omega. So, a dagger is a creation operator. This is an annihilation operator and this is a creation operator. And if you look at the expectation value of Hn in some state psi, since Hn involves a dagger k a k, this quantity is positive definite, this is greater than or equal to 0, whereas this a k lowers the energy by omega. So, there must exist a state such that a k acting on this state gives me 0. This annihilates, the annihilation operator annihilates this state. This I will call as the ground state of the system. Or I will call it as the vacuum. Now, once I have this vacuum, I can act on this, the creation operator on the vacuum, and this will give me some state which I will denote as k, whose Hn eigenvalue is omega. A dagger k will create a quantum of energy omega from the vacuum. Now, we can look at the momentum operator. You know the momentum operator is integration d cube x t 0 I. Here, right now I am just using this as a level, and this state is such that Hn acting on this state is omega acting on omega times k. Okay. Now, we will see why I have used this level k here. That is why I am considering this operator p here. If you substitute for the energy momentum tensor, what you will get is d cube x del L over del 0 phi times del I phi, and then you substitute for the fields phi, or this is equal to d cube x pi of x del I phi. You substitute for pi and del I phi and carry out the integration, then what you will get, I will not work it out, I will leave it as an exercise for you. What you can show is that this momentum operator pi will give me d cube k over 2 pi cube to omega times k I a k a dagger k plus a dagger k a k. So, this is an exercise for you, this is what you will get. Now, again I can write this as twice a dagger k a k plus commutator of a k and a dagger k. When I do that, there is a half here I think. When I do that, what I will get is d cube k over 2 pi cube to omega k I a dagger k a k minus half d cube k over 2 pi cube to omega times k I commutator of a k a dagger k. In the second term, this is a C number which is even when k goes to minus k, because this involves some delta function which is a even function of k, whereas there is a k I which is odd. So, when you carry out this integration, it will change sign when you so this quantity will be equal to minus of itself because of the appearance of k I here. Hence, this integration is 0. So, the second term vanishes identically. Therefore, what you get for the momentum p I is p I is equal to d cube k over 2 pi cube to omega k I a dagger k a k. Now, you take this momentum operator and you act on this state k here, then what you will get is not only that it has Hn eigenvalue omega, it is also an eigenstate of the momentum operator. If you act p I on this, then you will get k I. So, this state k is an eigenstate of Hn as well as p I with eigenvalues omega and k I respectively, and that is the reason I label this as k here, because omega, as you know, I am not explicitly writing, but omega is actually omega of k, which is square root of k square plus m square. So, it is sufficient to label it by the momentum of this state. So, what this operator a dagger k does is, it creates a quantum of energy omega and momentum k. Therefore, this state k here, I will interpret it as a one particle state with energy omega k and momentum k. So, these are one particle states. Similarly, you can add two such creation operators. You can start with the ground state and act a dagger k1, a dagger k2 on this. This will create two quantas of energy or of Hn eigenvalue omega 1 plus omega 2 and momentum k1 plus k2. So, therefore, this I will interpret as a two particle state. Similarly, if you act n number of creation operator on the ground state, then you will get n particle states. So, this is the way you can construct the entire spectrum, and you know what are its eigenvalues and what are its energy and momentum eigenvalues. The other important thing here is, if you consider the two particle state, let us say a dagger K1, a dagger K2 acting on this, because a dagger K1 commutes with a dagger K2, therefore, this is also equal to a dagger K2, a dagger K1 acting on the ground state. So, the state K1 K2 is identical to the state K2 K1. So, these particle like states, if you interchange two particles, you get the same state. Therefore, these are actually bosons, they obey Bose statistics. So, the particle like excitations in the Klein-Gordon theory are actually bosons, they obey Bose-Einstein statistics. Let us now go back to the full Hamiltonian. I told you earlier that I will come back to this Hamiltonian and discuss the second term, which I have not discussed in any detail earlier. So, the full Hamiltonian is Hn minus half d cube k over 2 pi cube to omega times omega times commutator of a k, a dagger k, right. So, let us look at the commutator here. We know a k and a dagger k prime commutation is given by 2 pi cube to omega delta k minus k prime. But here the argument is k in both these operators. So, what you will get in this commutator is a delta 0. So, the Hamiltonian H is Hn minus half d q k over 2 pi cube to omega times omega 2 pi cube to omega delta 0. When we considered this term for the momentum operator, it vanished because there was a k I here, which was an odd function of k, whereas here you have omega instead of k I. This is Hn minus half d cube k, this will cancel here 2 pi cube to omega. So, half d cube k omega times delta 0. So, there is no way this term vanishes, this term is still there and it is divergent, it gives you infinity. So, this of course does not make any sense. You do not want the particle states to have infinite energy. However, what really matters when you make measurement is the relative energies, not some absolute value of energy, but the relative energies between various states. So, when you do that, this term of course does not give any contribution. So, you just forget about the second term and you consider this to be the Hamiltonian. The other thing is, classically you know there is a well defined way on what you call to be the Hamiltonian, but when you quantize the system, you do not have the fields are not commuting functions, they are operators who have non-trivial commutation relations. So, you do not know what is the operator ordering to start with. So, there is an ambiguity on operator ordering, and you can resolve that ambiguity by saying that you order the operator in such a way that this term is not there. To be more specific, what we did is we blindly started with the Hamiltonian, which is half d cube x pi square plus grade phi square plus m square phi square, which is perfectly fine if you study classical field theory, but when you quantize these are operators and nobody tells you how these operators should be ordered. When you write these operators in terms of A case and A Dagger case, what you get is half d cube k over 2 pi cube to omega times omega A k A Dagger k plus A Dagger k A k, and when I rewrote this term, what I saw is that this is equal to h n minus half integration d cube k omega delta 0. This operator h n admits finite eigenstates, eigenstates with finite eigenvalues, but there is an additional term which gives you infinite answer. But this additional term is there because you started with a Hamiltonian which is this, but nobody tells you that the operator should be ordered like that. So, what you do is you define your Hamiltonian to be the one where the operators are ordered in such a way that the creation operators are to the left of the annihilation operator. If you do that, then both the terms are identical and this infinite term is not there. On the other hand, this Hamiltonian H n is nothing but the Hamiltonian, the old Hamiltonian H, where you look at all the terms and you shuffle these operators and then you put all the creation operators to the right and all the creation operators to the left and all the annihilation operators to the right. This process is known as normal ordering. So, you take this Hamiltonian H and you do normal ordering, you will get the Hamiltonian H n. That is why I have denoted this with a subscript n. N stands for normal ordering. And what you get is H n is, I will denote as normal ordering of the Hamiltonian H. By normal ordering, what I mean is you take d cube k over 2 pi cube to omega times omega times normal ordering of A k A Dagger k plus A Dagger k A k. This term, when you do normal ordering, this will give you A Dagger k A k, because here the annihilation operator is to the left and the creation operator is towards the right. So, normal order or ordering of this is A Dagger k A k, which is identical to this. Therefore, you get H n as a result. So, n of A k A Dagger k is simply A dagger k, A k. So, to state it again, if you start with this Hamiltonian, you get a spectrum where the eigenvalue of this Hamiltonian are all infinite, but if you subtract one term from the Hamiltonian, then you get a Hamiltonian which I have a new Hamiltonian which I have denoted as Hn, and this new Hamiltonian has finite eigenvalues. The spectrum is such that all the eigenstates have finite eigenvalues. So, we will start with this, we will take this to be the definition of the Hamiltonian here, and this is obtained from the old Hamiltonian by what I call as normal ordering, and the Hamiltonian that I obtained by normal ordering is known as the normal ordered Hamiltonian. What do I mean by normal ordering? By normal ordering, what I mean is I put all the creation operators towards the left of the annihilation operators. So, you take for example n such operators A k1, A dagger k2, A dagger k3, A k r, A dagger ks, and so on. When you do normal ordering, what it does is you just A dagger k2, A dagger k3, and A dagger ks, all these things are there to the left of A k1, A kr, and so on. This is what I mean by normal ordering, and when you do normal ordering, you get a Hamiltonian which has finite eigenvalues. So, we will resolve this ambiguity by saying that all the physical observables are normal ordered, whether we consider the Hamiltonian or momentum operator or any other operator, all are defined to be normal ordered.
Why does the normal ordering get rid of the infinity?
It gets rid of the infinity because the other term is not there. When you do normal ordering, you get Hn, and we have already shown you that this Hn is has finite eigenvalues.
How do we know this will always work? As in for whatever case that we might have?
Okay, so the first of all, you this is what you define to be your Hamiltonian, and what we have seen here, I mean, in this discussion is that it admits finite eigenstates with finite eigenvalues. Whether this correspond to a physical situation, whether you consider a physical system, and whether such a Hamiltonian explains any physical system or not is a question that we can discuss. So, there are systems, I mean all the systems that you know in quantum field theory are explained by such normal ordering, and then you can compute interactions and so on by taking the normal ordering Hamiltonian, and then you can compare whatever you get here with the answer that you do in real experiment. And if you find if your answer agrees with the experiment, then of course this is the correct Hamiltonian that you this is correct prescription. So, of course, it is not so simple, you cannot just throw the infinite term. The reason for that is although in a theory which does not contain gravity, adding a constant term to the Hamiltonian really does not have any consequence, but if you consider a theory of gravity, then of course the term that you throw from this Hamiltonian has finite energy. So, the energy of vacuum itself is not 0, it has infinite energy, and anything which has energy, any particle can interact with any other particle which has energy, it can interact gravitationally. So, therefore, it is actually not correct to add or subtract constant terms in your Hamiltonian in a theory of gravity. But if you ignore that fact, if you consider a theory where the gravitational interaction is negligible compared to all other interactions, you do not worry about this issue, and then you start with a Hamiltonian which is normal ordered. So, just to summarize, what we did is we started with a Klein-Gordon field and we quantized it, and then we have seen that the Hamiltonian can be expressed in terms of the creation and annihilation operators, which is d cube k over 2 pi cube 2 omega times omega a k a dagger k plus a dagger k a k, and to get finite eigenvalues we normal ordered this Hamiltonian. As a result, we got the normal ordered Hamiltonian to be d cube k over 2 pi cube, that is a half here, 2 omega times omega a dagger k a k. The momentum operator pi, normal ordered momentum operator, is the one where you have d cube k over 2 pi cube 2 omega times k I a dagger k a k, and we have constructed the spectrum. The spectrum of states are the ground state, which does not have any particles, and hence the ground state is the vacuum, and then one particle states are obtained by acting a dagger k on the vacuum. Multi-particle states are obtained by acting several of these a daggers, a dagger k1 up to a dagger kn on the ground state. These are multi-particle states. All these are eigenstates of Hn and Pi. I can introduce something which I will call as the number operator, which I will call as n of k as a dagger k a k, and the number operator is such that these states will have eigenvalues which are 0. This state has eigenvalue 0, this state will have eigenvalue 1, and so on. So, all these states in this spectrum will have eigenvalues 0, 1, 2, and so on, and these are known as the occupation numbers. So, the eigenstate of the number operator is the occupation number, and the Hamiltonian and the momentum operators can be expressed in terms of this number operator as Hn is this times n of k and Pi is this times n of k. All right. Okay, so we will close today's discussion here. In the next lecture, we will discuss causality and time ordering and propagator and all those things. All right.